And if you still remember, cross product, the direction is very sensitive to which two you apply. A2 and B3, A3 and B2 would have opposite directions. Okay? So therefore, for the first direction, you would have two components, but they are having opposite signs. Right? So if you condense all this into a matrix form, A cross B using orthogonal coordinate system will be extremely easy. All you have to write is the first unit vector, second and third, and then A1, the first component of your A vector, second component, third component, and B1, B2, B3. And then you just calculate the determinant of your matrix. As opposed to what you learned during high school, if you want to calculate A cross B, you have to find the angle, right? You have to find the angle, you have to take the sine, and you have to know A and B magnitude. So knowing the vectors and being able to express them using orthogonal coordinate system is very handy and straightforward, right? Now, take a moment and ask yourselves, we already know how to express A cross B vector. Now, let me remind you, A cross B results in a new vector. So now you have a new vector making an inner product or dot product with a third vector. The result should be a scalar, right? Okay, so think about it. How to properly write the matrix form when you have the scalar triple product. A cross B, you would have your first component, right? And then you make the inner product with the first component of C vector. So this results in a scalar in the first component, second component, and third component. So you end up with a scalar value. It's only a value, right? So in matrix form, for the scalar triple product, it's very similar to cross product between two vectors. All you have to replace is, now you just write down C1, C2, and C3. That's it. Okay, so these are very basic fundamental vector calculus, right? So let's move on. Today I want to focus on orthogonal coordinates. Okay, the reason will be very apparent because later we will talk about gradient. I know you hate it, okay? Gradient, divergence, and curl. All these three operations are fundamental and extremely important. So in the past, I know you just memorized the formulas for all three different orthogonal coordinate systems, but memories don't really last. Same for me. When I was a student, I was not able to really memorize everything for gradient formula, divergence formula, curl formula, but today I want to really teach you how to derive them. And being able to derive all those complicated formulations relies on your understanding to what I am going to teach you for the next 40 minutes. You have to understand about the orthogonal coordinate systems, its definition, and their resulting differential length, differential area, and differential value. Once you understand all these three parameters for three orthogonal systems, then gradient, divergence, curl are actually very straightforward. All right? So the first one is Cartesian coordinate. It's just a common x, y, z coordinate. that you guys used for the past 20 years. Okay? So in three-dimensional world, we can define a point using x, y, z coordinate. Okay, so I can express a point using their different x, y, z positions. Okay? Same for a vector. Once you have a position which is being expressed in Cartesian coordinate, your vector can also be expressed using Cartesian coordinate. For example, ax, ay, az in this case, you might have ax is equal to xy, ay equals yz, az equals y squared. Okay. So once you read this vector expressed as xy, you know the vector is having some positional dependence expressed in Cartesian coordinate, right? So the question is, once we express some position for a given vector using Cartesian coordinate, in this coordinate, how do we express the resulting differential length? What I mean is, I have x, y, and z. These are my three different axes. Okay. So if I allow to have some small change, starting from the point, a given point, P, it has x1, y1, and z1, right? All these position grids or values. I allow them to have some small change in x, y, and z directions. What type of three-dimensional object would I result in? In Cartesian coordinate, if I start with a certain point and I allow it to have some offset or shift in the y direction, x direction, and z direction, the result will give me a cubic, a very small cubic, right? So if we look closely at this figure, if we want to start from this location, this point, and we end up at the diagonal point, how should we travel? We should travel in the x direction, right? By a distance of dx, right? So we travel to here, and dz, and then dy, right? So on this cubic, if you want to travel across to the diagonal point, we have to travel by a distance of dx in the x direction plus dy, this is a distance in the y direction, and dz in the z direction. So in essence, if you want to move to the diagonal point on this cube, you have to travel total of these three distances sum. Okay? So the result is a vector. Okay, so this is called the differential length for a Cartesian coordinate. Now, this cubic volume has total of 6 surfaces. Okay, total of 6 surfaces. But usually we only take account of 3, the positive directions. Right? So this is the point I want to ask you. If I define my x, y, and z, x, y, and z unit vector, If I have an area or a surface which has a direction of positive x, right, pointing out into your eyes. If I know my small surface, differential surface, is pointing in the direction, in the positive x direction, how would its area be determined in Cartesian coordinate? This is the knowledge you accumulated from cross product, right? If your surface is having a direction, the direction is normal or perpendicular to your area, right? As a result of vector cross product. If the direction is in x direction, then its magnitude must be determined by the length in the other two directions. dz. Okay, so it must be dy and dz. So this is what I'm trying to repeatedly emphasize. A surface is a vector. It has its own direction and its magnitude. The magnitude is called the area. Once you know the direction, then the area will be determined by the other two magnitudes. So in this case, you have a surface which has a surface direction in the x direction, then its area must be determined by the differential length in the other two directions, dy times dz. Okay, so let's come back to the PowerPoint. So the other two differential areas would be, if you have a small square in the y direction, the direction is in y, then its magnitude must be determined by the differential length in the x and z direction. So y dx dz. If you have a square in the z direction, then its magnitude, the area, must be determined by dx times dy. Okay? This is a direct consequence of vector cross product that we mentioned last Wednesday. Okay? Everything are very straightforward and simple up to now because we're working in the Cartesian coordinate. So differential length, x direction, dx, plus y direction, dy, plus z direction, dz. Straightforward. Surface, once you know the direction, the magnitude will be determined by the other two differential length multiplied together. Differential volume. Well, you know how to calculate the volume for this cube. Straightforward multiplication of dx, dy, and dz. Straightforward. Okay, nothing tricky. Now let's move on to cylindrical coordinate. Oh, this is slightly tricky, but you have to remember, my methodology is I'm trying to emphasize differential length, differential surface, and differential volume. But before we do that, a formal definition of cylindrical coordinate. When we talk about a cylindrical coordinate, we are talking about some object, cylinder-like, like a cube, okay? So the points, any point on the surface of a tube can be defined easily by a radius, azimuthal angle, 方位角, azimuthal angle, and z. So z is identical to the z in Cartesian coordinate. Okay? In essence, we are talking about a three-dimensional object with a constant radius, but it can change in height, and then you can change in angle, right? So in the future, the unit vectors, A in the radius direction, I will just write the r hat. Okay? Radius hat means the unit vector in the radial direction. A phi, the azimuthal angle. I can write this phi hat. Z, just z hat. Right? So this position, you can also express a position using cylindrical coordinate. Then you see a bunch of radius, phi, angle, and z. You can also express a vector using cylindrical coordinate. Okay? So later, once we understand cylindrical coordinates, we can convert or transform between Cartesian to cylindrical coordinates, right? But up to now, let me ask you a simple question. I have ax, ay, az expressed in x, y, yz, y squared, right? If I write the same vector using cylindrical coordinate, I want to express this vector, the same vector, but I rewrite it somehow so it is defined using cylindrical coordinate. What would it look like? So the question now is, how to properly transform the vector into cylindrical coordinate. If you want to express this vector using cylindrical coordinate, you don't expect to see x, y, z, right? X, y, z are products, are results of Cartesian coordinates. If you express the vector using cylindrical coordinate, you would only expect to see r, phi, and z. So z is allowed, but you don't allow to have x and y. In cylindrical coordinate, you only allow r, the radius. You only allow phi, azimuthal angle, and z. Okay, so we have to learn somehow. But before we do that, let's have a clear understanding to differential length, differential area, and differential value in cylindrical coordinates. So if you start at a certain point on a cylinder, and you allow to have some differential changes along the three unit vector directions, you would end up with this type of three-dimensional object. It's like a pizza where you eat the inner slice first, right? The remaining of the pizza is like this. It's I don't really know how to call it. Really, I don't. Okay. So again, the question is, how can we walk from one point on this three-dimensional object to reach to its diagonal point? So we can start from this point and we walk along this path. So we initially have its initial radius, and then we increase the radius slightly by dr, right? So we walk from this point to this point, then we have r plus dr. And then we can change our height from z to z plus dz. What does it take for us to walk from this point to the final point? From here to here, are we walking along a straight line, or are we walking along an arc? This is a crucial point for you to remember, and I also noted on the PowerPoint. When the unit vector is an angle, then your differential length is not a straight line, but an arc. The length of an arc, 弧长, the length of an arc is radius dependent. So therefore, you have to remember the differential length is an arc when your unit vector is an angle. So this arc, the length of this arc is r times d phi. So although you have the same angular change d phi, but depending on your radius, the length of the arc will be very different. Okay? So if you want to buy a 6-inch pizza or a 12-inch pizza for the same price, you will always go for the larger one, right? Because it's bigger. Right? So therefore, the differential length in cylindrical coordinate, dl, a vector, would be dr in the radius direction plus, remember, when you have the unit vector as an angle, then your differential length is an arc. An arc is radius dependent. So you have to multiply this radius, r, by d phi. So you have a small angular change, but your total arc must be multiplied by the radius. Okay? Z direction is just dz times z. So the proper way to write down the differential length in cylindrical coordinate, you have to pay special attention. When phi direction is an angle, then the differential length is an arc. Okay? Now, differential area. Take some moment to write down the first one. For example, write it for yourself. How to properly express dsr. Remember, surfaces are all vectors. Your differential surface in the r direction, what do I mean? This one, for example, this guy. Okay. This guy, this area is having a surface normal pointing in the r direction. Right? In the r direction. Again, once you know its direction, the area must be determined by the other two differential lengths. So you need to have differential length in the phi direction, r d phi. This is the differential length in the phi direction, multiplied by the differential length in the z direction. Okay? So you can try it for ds phi, ds z. I'm trying to repeat this process so you can fully understand what I mean. The essence is a surface in vector analysis is a vector. It results from vector cross product. Okay? Of course, you have the answers in front of you. So when we talk about ds phi, this is the simple case because the direction is in the phi direction, right? So the area must be determined by the differential length in the x and z direction. X and z are both not angular, so we don't have arc. So it's direct multiplication of dr and dz. Right? On the other hand, when you have a differential surface in the z direction, dsz direction is in the z direction, so the magnitude must be determined by the differential length in the phi direction multiplied by the r direction. So you have to be very careful when you have the phi direction differential length It is an arc. An arc is radius dependent. So you see this, these two are having radius dependence, but not this one. The surface pointing in the angular direction, the size is not radius dependent. Okay? You don't see the radius in there. Alright, so differential value, multiply them together. You multiply this one, and this one. Okay? You have the differential value. So are we clear up to now? I'm taking this extremely slowly. And the reason is, to me, the ability to fully understand and not having to memorize the formulation for gradient, divergence, and curl relies on your understanding to the most basic fundamental definitions. Okay? So hopefully today, by the end of the day, I can show you why I'm focusing on this so much. Right? Now you have to think, well, eventually, a given point is a point, right? For example, this point is this point, but I can freely determine whether I want to express it using Cartesian coordinate or symmetrical coordinate. It's my choice. The point does not change. How to express it can be changed. So the question is, are we able to freely convert or transform that given point coordinate by using Cartesian or symmetrical definitions? Right? So I'm now showing you the relationship of the four unit vectors. X unit vector, Y unit vector, R unit vector, and phi unit vectors. I'm showing you this four. Why only this four? Because Z are both common. Z are identical for Cartesian and symmetrical coordinates, so they don't need conversion. This is the point you need to rely on your understanding and ability for performing inner products, dot products. R unit vector might be making some angle phi with X unit vector. Okay? So the meaning of dot product is to find the projection, right? If you want to express the R unit vector as X unit vector and Y unit vector, you only have to project them. Project it onto both. Okay? So if you want to project the R unit vector onto X unit vector, you have cosine. And the R unit vector as projected onto the Y unit vector is taking sine phi. Okay? So that's what's being listed here. So R unit vector making a dot product under this definition of phi. The phi is the angle with X axis, always. Okay? Phi is defined as your radius making the angle with the X axis. And therefore, if you want to make the inner dot product or find the projection of R unit vector onto Y, you have sine phi. So these are extremely important because understanding this allows you to convert between the two coordinate systems. On the other hand, phi unit vector, when it projects onto the Y unit vector, is straightforward. You take the cosine. But Y projected onto the X is now having a negative sign, right? Positive X is defined downwards, but you see this A phi is pointing upwards. So it is having a negative sign, and it takes a form of sine rather than cosine. So a phi projected onto x unit vector takes on a negative sign in the form of sine phi. But a phi projected onto the ay unit vector, straightforward, just cosine phi. So whenever you are on your examination or in the future, you're trying to do some derivation, you have to be able to draw these 4 unit vectors. And everything is straightforward. You don't have to memorize anything. Okay? But just for your reference, let me write down these 2 equations for you because we are going to use it in the future. Okay, we are going to use it in the future. So being able to convert or transform from one coordinate system to the other is nothing more than just understanding the basic definition of a given orthogonal coordinate system. Okay? And then you can compare the unit vectors between 2 systems. And then you can just freely convert. Okay, so let's come back to the PowerPoint. Let's try to convert the positions. Okay. Suppose I know a position expressed using cylindrical coordinate. Can I transform it into the Cartesian coordinate? When I first expressed a given point in cylindrical coordinate, it means I know its radius, I know its hypotenuse angle, I know its height, z. But somehow I don't like it. I want to express it using x, y, z. Is it possible? Of course. If you like it, you can do it. So let's understand about this point. So this point, we know its radius, we know its azimuthal angle, so we know how to express its corresponding x value and y value. X is just r cosine phi, y is r sine phi, right? That's all you have to do. So now you can convert the point initially expressed in cylindrical coordinate, but now using these expressions, right? It's now in Cartesian coordinate. Likewise, when you initially define a point in Cartesian dimensions, you can also change it to the symmetrical coordinate. Because once we know the points x, y, and z, this r, the radius, is just x squared plus y squared, and take the square root. And phi is just the ratio of y to x, and you take the tangent arc. Okay? Z remains unchanged. So these are extremely easy. Changing between the point position between 2 coordinate systems are straightforward. But what about the vectors? Take a good look. As I mentioned, a vector can also be expressed using whatever orthogonal coordinate system you like. Okay? So what I'm saying is, this A, vector A, can be written down in the form of Cartesian coordinate but it can also be written down in the form of cylindrical coordinate. It's the same vector, but only expressed in two different ways. So for example, if I already give you the vector expression using Cartesian coordinate, like the one I wrote on the blackboard. All right, let's walk to the blackboard. I initially gave you the property expression of ax, ay, and az. So basically, I defined the vector, but using Cartesian coordinates. So you see a lot of x, y, z, and y squared, right? But they are not proper as the expression for cylindrical coordinates. So you have to convert. So how to do the conversion? Again, I'm showing you this. The proper conversion relies on your understanding of the relationships among the four unit vectors, but which is already here on the blackboard. I wrote it, I copied it down for you. Okay. But what is the methodology? How should we approach this problem? The ones in blue is something you know it already. Okay. Suppose I gave you the vector expression in Cartesian coordinate. How can we find out the resulting AR, A5, and AZ? So this is the point you really have to think and try to understand the basic meaning of orthogonal coordinate systems. What if I make a dot product to A? What happens if I use one of the unit vectors and I make an inner product with A? For example, if the entire A vector is making an inner product with AR, I would extract this AR component, right? Because by making inner product of the radius unit vector, these two vanishes, right? These two are just gone. They're orthogonal. You only extract this component. Okay? So I know how to extract the AR component. This is what I want to have, right? I want to transform the vector in Cartesian coordinate into the cylindrical coordinate. So I need to be able to write down AR, A5, AZ individually. So the process, I extract this one by making an inner product of R unit vector to A. So on the right-hand side, I only have AR. But for the blue stuff, this is a direct inner product of my original vector expressed in Cartesian coordinate, but now making an inner product with the radius unit vector. So this is where the transform begins. Okay? So smart students, when you perform this inner product, how many terms do you have? Ideally, you would have 3 terms, but in the end, because R unit vector is orthogonal perpendicular to Z, so in the end, this one is not there. So all you have is AR. AR component is now contributed from the sum of AX plus AY components, but with certain scaling factor. And those scaling factors, we already know. Why? Because I'm such a nice teacher, I wrote down this for you, right? I taught you, and I wrote it down for you. Because R, X, Y, all the relationships, all the inner product, all the projections are known. So R unit vector making inner dot product with X unit vector is cosine. R unit vector making the inner product or the projection onto the Y unit vector is sine phi. Okay? So if you can compare the PowerPoints and the Blackboard, this is what I emphasized. All the conversions relies on your understanding, your deep understanding to the 4 unit vectors. Once you know their relationships, you know how to do the conversion. So that is AR component is coming from both AX and AY, but with a strange fraction or scaling factor. AX times cosine phi, AY times sine phi. Okay? We can repeat the process to extract A phi. Do we need to extract for AZ? AZ? They are the same, right? They are the same, so you don't have to extract. When you're trying to transform from Cartesian to cylindrical, or cylindrical back to Cartesian, you don't have to worry about the Z component because they are identical. So we can repeat the process to extract the A phi. How to extract A phi component? You only have to make inner dot product. Okay? The dot product of the entire vector with phi unit vector. Right? So you only extract this term. And that's equivalent to saying the Cartesian vector is now making an inner product with phi unit vector. But that we already know, right? We already talked about. So phi unit vector projected onto X unit vector is negative sine phi. This one is cosine phi. Okay. So in the end, there's a very simple table or matrix form allowing you to do the transformation. If you know your vector in the form of Cartesian form, you just write down AX, AY, and AZ, and then multiply by this matrix, and then you have AR, A phi, AZ. But remember, you have to express all these x, y's, y, z, y squares using also the transform way. Right? So x is r cosine phi, y is r sine phi, so let's just do this for you. So A R equals, so x is r cosine phi multiplied by r sine phi, and then multiplied by cosine phi. So it's squared. Right? A1 is y times z, so it's r sine phi times z, but you have to multiply the additional sine phi. Okay. AZ is y squared. But when you transform the vector into a new coordinate, you don't want to see x and y, right? So this is r sine phi squared. Simple. But ask yourselves, can you get it right if we have an examination in 10 minutes? Probably you get 0 points. Okay? So try to absorb what I taught you up to now. Okay? Let's take a 10 minutes recess. But during this 10 minutes, try to think, what is my methodology? I'm merely using the definition of orthogonal coordinate systems, the unit vectors. I'm only trying to draw these 4 unit vectors, and that already allowed me to freely transform between the 2 systems. All right? Let's take a 10 minutes break. regarding what I taught you for the last 15 minutes? If not, let's try to finish spherical coordinate. So usually students are having the most trouble, most problems with spherical coordinate. So by definition, right, just as the name implies, if we have a spherical object, what is the easiest way to define a point on that spherical surface? We can define it by a constant radius. Okay. Now, as you can see, the radius in spherical coordinate, I like to use the capitalized R letter. Okay. So, any point on a spherical surface, I can use a well-defined radius and then with the inclination angle. So inclination angle is your radius to z axis. Okay, so that is theta, inclination angle. I also need another angle which is identical to the cylindrical coordinate, the azimuthal angle. So basically, I have the radius, I have two angles. Like one angle is in this direction, another one is the angle on the xy plane. Okay. So r, theta, and phi. Again, theta is the angle between your radius vector and the z-axis in Cartesian coordinate. But in spherical coordinate, you don't really have this z. You don't. Okay? This is only for you to know. So later on, I will switch between this writing system or this writing system. But whenever you see this capitalized R with a hat, you know you're working in spherical coordinate system. Okay? So R, theta, phi, AR, A theta, A phi. Remember, the most important knowledge for you to understand about spherical coordinate is when your radius, where is your radius? This is your radius, right? This radius is the three-dimensional radius. But if we make a projection of that radius onto the xy plane, you also have a radius, right? We can make that projection by this capitalized radius multiplied by sine theta, meaning you're only trying to find this radius, okay? So once you project that onto the xy plane, this r sine theta is the not capitalized r in cylindrical coordinate. Let me use this picture, okay, to better illustrate my point. This is my projected radius onto the xy plane. Okay, so basically, it is r times this is theta, so this is r sine theta. Okay, this is r sine theta. By making this r sine theta, I know my radius on the xy plane. Okay, why is this important? Let's continue. Differential length. Again, differential length means I start with one point on this three-dimensional structure. How can I walk to the opposite diagonal point? In a spherical coordinate, your unit basic structure is very complicated, but again, we can start with one point and we add a differential radius dr, right? We add a differential radius dr, we arrive at this point, or okay, we start from here. We start from this point, we add dr, we arrive here. Now we want to walk to this point and then to this point. The problem is this segment, is it a straight line or is it an arc? We're trying to change the angle by theta plus d theta, right? We're changing the angle, but because we have a radius, so basically we are spanning an arc. So again, when your unit vector is an angle, your differential length is an arc. So this arc length is r times d theta. Okay? So this is an arc. It is radius dependent. Now, what is the arc length from here to here? Because from here to here, we're changing in phi angle. Phi plus d phi. Again, we have angular unit vector, so the length spanned is an arc. So then you have to think, oh, what is the proper radius for this arc? Like I mentioned, this radius is r sine theta, the projected radius onto the xy plane, right? And then we make d phi. So in essence, differential length in spherical coordinate, you have in the radius direction multiplied by the differential radius. Now you have two unit vectors that are angular. So each one would give you an arc. In the theta direction, you're using the entire three-dimensional radius to span this arc length. So it's capitalized R, the radius, multiplied by d theta. But in the phi direction, only the effective length projected onto the xy plane, r sine theta, is used to span this arc length. So, in the phi unit vector, even though you have a differential azimuthal angle change, you're multiplying with its r sine theta. This is the smaller non-capitalized r in cylindrical coordinate. Okay? So are we clear up to now? Usually, you're most confused with spherical coordinate systems. And the reason is you don't really understand why I need to multiply this sine theta. Because we're trying to find this projection onto xy plane. Okay. So once we know differential length, we can write down differential area. Try it on your own. For example, if I want to properly express this surface in the r direction, capitalized r direction, capitalized direction dsr, in the capitalized r direction, if your surface is in the r direction, its area must be contributed from the other two differential length. And in this case, you have r d theta multiplied by r sine theta d phi. Right? The other two differential lengths are both arcs. So you have to properly write down their corresponding radius, and this is the radius that you used in cylindrical coordinates, r sine theta. Okay, so let's come back. This r sine theta is the non-capitalized r in cylindrical coordinate. Right? So it's quite messy, But try on your own. If you understand what I'm trying to teach, what I'm trying to convey, you can get it right. Differential value, you just multiply the three differential lengths together. It's no problem. Okay, so now, this page relies on your efforts and your devotion. This is the beginning of a successful transformation from spherical coordinates to the other two coordinate systems. So you need to be able to convert, right, or express r, theta, phi unit vectors using Cartesian coordinate, for example. Okay, so you need to be able to draw the relationships. Okay? So I'm leaving this page, I'm giving you the answers, but I'm leaving the works for yourselves. Okay, so let's not occupy the time of the classroom. Position transformation is also straightforward, so I'll just go over the results. Okay, so if you have a position which is given in spherical coordinate, you can transform it into Cartesian coordinate, x, y, z, because we know that x, this is a point again. This position on a spherical surface, if you want to find its x and y value, you first need to perform the projection onto the xy plane, right? And I mentioned this over and over. When you do this projection, you're trying to find this green radius, non-capitalized r, which equals to capitalized R times sine theta. So once you have this r value identical to the symmetrical coordinate, everything is similar to the symmetrical coordinate. Okay? So this is what you have. So once you have this, you are free to convert from spherical coordinate into Cartesian coordinate. And likewise, you can do the same thing. So this is straightforward. I'm leaving the contents for you to verify on your own. Again, vector. If you can convert for positions, you need to be able to convert for vectors. And you are using the same steps. A given vector can be expressed in Cartesian form or in spherical coordinate form. If you already know its Cartesian components, you can extract the spherical coordinate components by the same methodology I just taught you. You just make the dot product of the entire vector with some unit vector in the new coordinate system. Okay? And based on the knowledge I just wrote down for you in the previous slides, right? AR, A theta, A phi can all be expressed by unit vectors in other coordinate systems. Here, AR, A theta, A phi can be properly formulated by the unit vectors in the Cartesian coordinate. So once you know this, basically, the transformation is straightforward. Okay? So I'm leaving this page for you to work on your own. If required, if a lot of students ask, I will have the TA to really walk you over this transformation for you. Of course, online using streaming again. Okay. The TA is very angry now. So in essence, what I taught you up to now is nothing more than trying to emphasize the differential length for an angular unit vector is an arc, right? You see this over and over. So the differential length in a generalized form, the L is in the first unit vector direction with the first differential value multiplied by, this is known as Jacobian in your past, right? You all passed engineering math and you all learned Jacobians. Jacobians, for Cartesian coordinate, you're very lucky, 1, 1, 1. Cylindrical coordinate, you have 1 Jacobian. Why? Because in this degree, phi is angular. So your differential length is an arc. You have to multiply this by d phi. Okay? Spherical coordinate, unfortunately, your second coordinate is theta, angular. Third one, phi, is also angular. So you need to take their effective radius into consideration. The first one, in the theta direction, fully r. In the phi direction, you're making a projection onto the xy plane. So only r sine theta, not entirely r, only the sine theta component contribution. Okay. But let me emphasize again and again. This capitalized R projected onto the xy plane, the effective radius is equal to the non-capitalized R in the cylindrical coordinate. Okay. So differential area, generalized form, you always have this Jacobian. Differential value in that form. So what have we learned? What have I taught you? Understanding differential length for all three orthogonal coordinate systems is extremely important. When your unit vector is an angle, your span differential length is an arc. So you need to properly multiply that differential amount by its radius. Okay. So this will be used for gradient, will be used for divergence, it will be used for curl. All right, so are we clear up to now? Do we have questions? If not, let's go to the next PowerPoint set. Okay, so we'll take a moment. Okay, so we're marching into the second PowerPoint set for vector analysis, and this one is titled as Vector Calculus. So we're focusing on gradient, divergence, and curl operations. Believe it or not, there's actually a book just focusing on divergence, gradient, curl, and all that. So if you're interested, you can read that book. But usually, to my understanding, all the engineering students really hate math, so you're not going to read that book. Today, for the next 30 minutes, I only want to emphasize on one single operation, gradient. Okay? Even though we have time, we're not going into divergence. I only want to focus on gradient. And I really want to show you the importance of understanding the differential length for all three different orthogonal coordinate systems. So, what is a gradient? You have to understand the operation based on whether this operation is working on a scalar function or a vector function. So by definition, well, let's take a real life example, what we already learned. We have y equals f of x in one dimension, right? We only have one variable, so it's a one-dimensional function. We have this beautiful blue plot, right? What we learned in the past is how can we find the rate of changes to this plot? The rate of change, by definition, think about it, is just the slope, right? So how to find the slope of this trace for each point? You make a differentiation, right? For example, at this point, we know the slope. After you perform the differentiation, you have this red line. So at this point, you have a positive slope. At this point, what would your slope be? 0, right? So at this point, the rate of change is 0. At this point, the slope is negative, right? So you can find the slope. But what is the benefit of knowing the slope? Let's take a look at this map. This is a two-dimensional map. Okay. So imagine this is the map of our humanity college. We have a mountain, right? So this is like telling you the heights. The contours are having the same height of our humanity college. So if you are a student and you have to take classes at our humanity college every day, maybe twice per day, and you have to walk to Xiaochibu for lunch, which road would you take? Are you going to take this one, or are you going to take this one? What's the difference? All these connected lines are saying they are having the same height, 400 meters, 300 meters, 200 meters. So for me, if I only walk up there once per day, I'm old, right? My legs are really not so powerful anymore. I like to take this road. Right? Eventually, I will reach the College of Humanity, but I have to walk for a longer distance. So why am I choosing that path? It's because the slope is not so steep. So I can walk easily, even though I have to walk for an overall longer distance. So this is the path where the rate of change in height is the smallest. For you, like my TA, she's very young, she's only 20 plus. She'll prefer to take this path, right? You start from 100 meters and you reach to the College of Humanity in a very short distance. So if her legs are strong enough, she could reach and take the class within maybe 5 minutes. But I have to take 20 minutes in walking. So her choice is to take the path where the rate of change in height is maximized. Okay? So now I'm going to define, I'm using a live example to tell you what is the meaning of gradient. A gradient is trying to do some operation on a scalar field. Heights are scalar, right? Heights are scalar. But after you take the gradient of this heights, you arrive at a vector because you have directions. Like the slope, you have going up, you have going down. Okay? But the meaning is the gradient is trying to find a vector so that along the gradient direction, if you take that path, this red path, you are guaranteed to change in your height in the shortest distance. In other words, when you find the gradient, you are trying to find the direction and path with the maximized change in that scalar function. Okay? Point by point. So this is the official definition, mathematical definition for gradient. But the meaning is, let's come back to this two-dimensional map. We have the constant height contours. If we perform the gradient for this map, we can find this red path as our gradient, showing you this is your shortest path to achieve if you want to take the class. All right? So, again, remember, gradient, this gradient operator, a inverted triangle, you pronounce it by del, okay, like del, okay? Del V, V is a scalar function. After you perform the gradient operation to this scalar function, you arrive at a vector. And by definition, you're trying to find the change of your scalar function in that shortest path. So you perform the gradient, you find the path where you can change your V in the shortest distance. Okay? So what is shown here are two equal potential surfaces. Right? This is V1, this is V1 plus dV. Think of V as your potential or height. This is height number 1, height number 2. So if you perform the gradient, you would have this direction or this path. This is called dN, which is normal to the equipotential surface. Right? The normal direction takes on the shortest distance. So if you take the gradient to the height, the gradient will be positioned or oriented in this direction, P1 to P2, telling you this is the shortest path to climb from level 1 to level 2. Okay? Just like the case I showed you. But if you prefer to take another path, like P1 to P3, is it okay? Of course it's okay, it's your choice. But you can reach from this level to this level along a longer distance, so you have to walk longer, it takes more time. But if you prefer, why not? So I'm using this knowledge to derive gradient formula expressions for all three orthogonal coordinate systems. So be very careful. Definition of gradient to a scalar function results in a vector. Okay? So you're trying to find the maximum rate of change in your scalar function along that particular shortest distance. What happens if you want to take this path? This is the gradient direction, but you want to take another path, P1 to P3. So the distance for P1, P3 segment is called dl, right? dl. How are dl and dn related? dn means the shortest path. dl is my personally arbitrary chosen path. So dl and dn as compared will be divided by cosine alpha. Alpha being the angle between the two paths. Is it reasonable? Anything divided by cosine will be longer, right? Because cosine is limited to smaller than 1. Okay? So this is reasonable because this is the direction with maximum change, so the path will be the shortest. If I don't take this path, then my distance will be longer. So the change will be small, right? So this is okay. So my dl, my chosen path, is longer than dn, reasonable, because it's divided by cosine alpha. Then I want to examine what is the rate of change in v when I take this path? dv along this path. Well, basically, the rate of change along this path is more gradual, right? Less steep. Therefore, it is multiplied by cosine alpha. This is coming directly from here, right? But during this process, what I'm trying to teach you is the way to confirm your mathematical equations. The rate of change in v along one potential path and the steepest path, in this case, would be smaller, right? How to maximize it? Make alpha equals to 0. Then L is equal to N. You're walking in the fastest. Okay? Okay, up to now? All right. So now we can write this expression. What is cosine alpha? Cosine alpha is coming from the fact the dm path and dl path are not parallel. So the cosine alpha is coming from the inner dot product of an unit vector and dl unit vector, and then multiplied by the absolute value of gradient v. Right? You still remember the definition of gradient v is dv dn and multiplied by a unit vector. Okay? So this one, an and the absolute value of grade v, del v, is gradient, making a dot product with my chosen path unit vector. So what does it mean? It means if I take on my personal choice of path, then the rate of change, the change in my scalar function, would be the gradient making an inner dot product with my differential length. Think about it. Does it make any sense? Gradient of v tells me I can get the maximum amount of change in v along this particular path. But like you, students, when your parents tell you to do this, you don't want to do it. You want to choose another path, right? Your parents tell you to go to Jiao Tong University, you come to Tsinghua University, and you make the right choice. So you want to take another path, but the price you have to pay is you have to pay more work. You have to do more work. You have to walk for a longer distance in order to reach the same change in V. Okay? So you come from point 1, you reach to point 2, which is on this height. P3 is also on the same height, but you have to walk longer. And that is taken effectively by making an inner dot product to dl, the differential length. Because when you perform the inner dot product, you have cosine alpha, right? It's always smaller. So this is telling you it's fine for you to take this path, but your change every step is smaller as compared to you take this path. Makes sense? Okay? So why do I want to spend all this effort in teaching you such a simple formula? This is extremely useful for you to understand gradient in 3 different orthogonal systems. dV is the change in V in certain coordinate system. dl, we spent lots of time on dl, differential length, right, for all 3 different orthogonal systems. So if we're working in different coordinate systems, once we know this proper formula for dl, then we know gradient of v for that given coordinate system. So let's go over them. If I first try to express everything, v, dl, in Cartesian coordinate, dv, my change in the scalar function in Cartesian coordinate, is a partial differentiation of v to x and multiplied by dx, plus scalar function making a partial differentiation in y and multiplied by dy, plus in the z direction. Okay? So this is straightforward. This is not coordinate dependent. dl, do I know how to write down differential length for Cartesian coordinate? Yes. We spent 40 minutes on it, right? So this is x direction times dx plus y direction times dy plus z direction dz. Straightforward. So now, ask yourselves, you know the answer to the left-hand side, you know partially the answer to the right-hand side, but now you want to make a scalar, a vector, dot product of this dl to gradient of v, also a vector, and you have this answer. What would your gradient be formulated in Cartesian coordinate? This is the most straightforward way to derive the gradient formulation for Cartesian coordinate. You compare right-hand side to left-hand side, scalar, eventually scalar making a gradient becomes a vector, vector making an inner dot product, so you must have the x component, the y component, the z component, right? So by definition, it tells you gradient of a scalar function must be a vector. Otherwise, you cannot make a dot product to another vector. So the gradient of v is itself a vector, ax, ay, and az, and the x component must be the partial differentiation of v to x. So this one multiplied by this arrives at this term. The y component, making an inner dot product, the y component of the differential length gives you the second term. The z component of the gradient, making an inner dot product, to the z component of the differential length gives you the third term. So do you already see the flavor? Once you master this process, once you understand dl as expressed in all three different orthogonal coordinates, you immediately arrive at the proper mathematical formula for that coordinate system, at least for the gradient. Okay? So this is the basic formula we're using. The change in my scalar function is the gradient in making a dot product to my chosen path. The path, differential length, is also the length is the vector. So this relies on your basic understanding to dl. Okay. Cylindrical coordinate, I can just write down dv in cylindrical coordinate is nothing more than the partial differentiation in the r direction multiplied by dr, and the partial differentiation in phi direction in times d phi, partial differentiation in z direction in times dz. So these are straightforward. You don't have to remember anything, right? The change is just the partial differentiation multiplied by the differential change in that unit vector direction. This is equal to gradient of the scalar function in cylindrical coordinate, making an inner dot product with the differential length in the cylindrical coordinate. Remember, when we're talking about phi direction, the unit vector is an angle. The differential length is an arc. So you have r times d phi. So now by direct comparison, something in the r direction, the r component of the gradient v in cylindrical coordinate will give you this one. So it must be in the r direction, simply del v del r. But it's weird. The second term, you have r times d phi multiplied by something, the r is gone, right? There's no r in the result, so you have to divide by r. So gradient of v in cylindrical coordinate for the phi component, you're making del v to del phi, but then you have to remember you have to divide it by r. Why you have to divide it by r? Because here in your dl, you have a multiplication of r. So this r times this 1 over r gives you this one. Okay? So this is the most straightforward way. So once you know this, there's no need for you to memorize anything. Right? Spherical coordinate, again, spherical coordinate, dv is simple, right? You have your partial differentiation multiplied by your difference in r, theta, and phi. And in this case, the differential length for spherical coordinates is more complicated, but it's not so complicated. You only have to consider the two arcs. In the theta direction, the arc length is the entire radius multiplied by the theta variance. In the phi direction, the effective r is not the entire radius, but r sine theta, right? And then times d phi. So once you have this arc being considered in your DL, your gradient has to divide by it. That's it. Okay? So you compare this one to this one, you must have this proper formulation to arrive at dV. Right? Is it clear? So the generalized expression for gradient of a scalar function for any orthogonal coordinate system is just 1 over h1, the Jacobian, 1 over h2, 1 over h3, and then you have the partial differentiations. Okay? What are the Jacobians? The radius for the arc. So basically, h1 is always 1. h2 for the cylindrical coordinate is r. For spherical coordinate is capitalized R. h3 cylindrical coordinate 1 r sine theta for spherical coordinate. So I know a lot of you learned this for your first year of physics, maybe, or for your calculus. So it's very confusing because gradually over time you forget, you divide or you multiply. Right? But having understood this, the meaning of, I'm starting from the meaning of gradient. Gradient gives you the direction and path where you have the maximized change. But if you take another path, then your change will be smaller. So it makes sense to make the dot product of your chosen path to the gradient. Because when you make in the dot product, you have the two absolute value multiplied by cosine. It makes it smaller, right? Makes your change smaller. So in the future, all you have to remember is the meaning. This is the meaning. You start from the meaning, and you start from your understanding to differential length. You don't have to memorize anything. Okay? So my goal is after my class, you really don't have to memorize because memories are short term. After the semester or after examination, you return everything to me, so I don't need to remember it so much. Right? Okay? So we still have 2 minutes. Are there questions from the students? How many students online? Tell me more than 30.
No.
No? It's okay. I'm not depressed. Alright, so if we have no question, on Wednesday, we are going to adopt the same methodology for divergence and curl. So do prepare to come into the classroom. Alright, thank you.